All right. If you are new, feel free to raise your hand or come off mute. Um, Otherwise, if you want to, drop in the chat your name and pronouns, organization and title, uh, so we can see who's all in attendance. I will pass it to David.
Perfect. Thanks, John. Hey, folks. David Smedick, he, him pronouns. I am a senior manager on the NEAP team, Technology Market Transformation team. I'm new to NEAP. This is at the end of my third week. So diving right in. Appreciate it. And I'm based out of Baltimore, Maryland. Prior to NEAP, I was with the RMI Carbon-Free Buildings team. So in the space, just on a slightly different angle, was doing a lot of federal policy work at the time. And yeah, excited to be here. So we're with Tara, who's also on the call, and Dave Liss.
Thanks. Welcome. And welcome to NEAP, I guess. Sure we'll interact in projects and other forums. All right. To refresh everybody, we are talking primarily about air-to-water heat pumps with a bit of a residential size focus. Our topics may overlap with hydronic heating, hydronic cooling, combi systems, thermal storage. There's all sorts of things we can talk about when air-to-water heat pumps are in the mix because of how flexible they are. Let's keep on rolling. Okay, so if you have anything new, links to reports, presentations, materials, or you want to give a brief update on any activities, wins or losses, feel free to do that now. You can either raise your hand or drop a link. In the absence of that, though, I did want, I'll pass it to Peter in a second. I did want folks to also update us and advertise your fall conference presentations. We're moving into fall conference season. There's 6 different conferences or 8 different conferences across the next month and a half, or maybe 2 months. So if you are presenting on air-to-water heat pumps, this is a great time to tell everybody to go see your presentation wherever it may be. Yeah, Peter.
Yeah, so just on the topic of announcements or updates. So at LBNL, we have started interviewing industry experts around the temperature requirements for hydronic heating systems in residential buildings, especially those using radiators. We're starting to reach out to people scheduling those interviews because we want to understand what the industry expects and why. And several of you are on the list of people to contact, but just in case, if you think that you have a lot to share on that topic, please don't hesitate to reach out and we'll make sure to include you on the list.
Thanks, Peter.
Thank you.
All right. Anybody dropping anything interesting in the chat? I can give Chris. Yep.
Hi. Briefly, we are hoping to begin a project soon where we're going to look at sort of the testing and implementation requirements for air-to-water heat pumps when used in existing buildings that have hydronic systems, primarily in the Northeast. And so it's not a done deal yet, but it looks pretty good. And part of that will also be reaching out to the German industry and finding out what they're using there, because they're probably a few steps ahead of us in terms of levels of implementation.
I've read papers out of Europe about getting to this topic that Peter was bringing up about replacing distribution, replacing radiators, and it's a topic that I'm interested in as well. All of the sites that we selected for our pilot have in-floor radiant, but there's a lot of radiators out there, a lot more than there are in-floor radiant heating homes, and so if there is some way that we can build up our knowledge and expectations as an industry and build confidence in the contractor base and doing those replacements, I'd love to see that.
You know, the German Heat Pump Association, I believe, is developing guidelines for existing homes, you know, with hydronic systems that use radiators, and how to determine whether heat pump water heater, you know, an air to water heat pump can be used without radiator replacement or upgrades, or whether additional measures are needed, you know, whether that's building shell improvements or what.
Yeah, great. Thanks, Chris. On my end, our pilot now has 4 full installs complete, 2 of which are dual fuel, which is interesting, in Wisconsin, and we're monitoring across this upcoming winter. We were hoping it was going to be last winter, but some of those installs didn't get in until the late winter, early spring. And the new construction one didn't happen until the summer. So stay tuned for results there. Anyone else have an update?
John, on the conference front, you have a note there for the hot air water forum. If there are people that have residential retrofit results, I think the home performance conference, a lot of the, you know, weatherization audience professionals, etc., they're accepting abstracts. I think they just extended that through next week, so might be a forum for folks if
This is
in the retrofit.
NHPC.
Yeah, exactly.
Thanks, Jason. Jeremy?
This might be good for a gasp or a chuckle, but I decided to take advantage of the heat pump tax credit and replaced my CAC with a cold climate heat pump, but my duct system isn't big enough to cover my full heating load. But given the cost and performance and basically unavailability of air to water heat pumps in the DC area, I put in a electric resistance backup via a 30-gallon water tank. So anyway.
Unfortunate, but
yeah,
water heat pumps are expensive.
So next step in a few years, hopefully next generation, hopefully I'll be putting in a air to water heat pump.
So Jeremy, it's Mark from LG. I have a question. Why did you say something like relative unavailability?
Well, I haven't been able to find anyone to install one for me.
Really?
Yeah.
Huh. Well, that's on companies like us. So I've got to, I'll talk to you later or we'll figure that out. But we have active distributors and contractors in DC and the DC area. And I'm sure other manufacturers do as well. So that's a little disconcerting. Did you contact Vic, who runs the DC SEU programs?
You know, I don't know him.
No,
so
Vic
no, I did
it's
not.
VEIC, it's Vermont Energy Investment
Oh,
Corp.
VEIC.
Yeah, they're the implementer for the DC SEU programs.
Yes, I know of DC SEU. I didn't know that they had anything specifically with Hydronic.
We can cover
I'm
this
happy to
later.
follow up.
Yeah. Feel free to
yeah.
chat offline about it. I want to keep
Sure.
things moving. I wanted to note that next week the hot air and hot water forum call for abstracts is going to come out. I assume the due date will be after our next meeting, and I am kind of thinking on ideas that we could tackle as a group and use one of our working group meetings as a session to brainstorm or build something. So if you have ideas, please email them to me or chat about them in the chat today during the group meeting. I know that other working groups that I've seen have sometimes put together you know, interesting content that they then present at the forum. Or if you can think of, you know, an event you'd like to have at the forum or a meetup, let me know, and I'm happy to help facilitate that or move those ideas farther towards reality. With that, let's move along to our presenter. I will relinquish control. Can you present Jason? Looks like you can. Okay, great. Thank you so much, Jason, for joining us and presenting on behalf of GTI. We appreciate it, and I'll turn it over to you to talk about air water heat pumps and lab and field research.
Yeah, great. Thanks, John. Happy to share a little bit of the work that we've been doing in the space. I'll do a kind of an introduction, but real quick, have my colleague on the line, Alejandro. You want to do a quick introduction? You might have some input on some of the technical questions later.
Yeah, sure, Jason. Hi, everyone. My name is Alejandro Guada. I'm a principal engineer, GTI Energy. Developing a lot of different programs and evaluation method of tests for, complex systems such as the one we're about to present to better understand how systems really perform in as installed conditions. So looking forward to talk more about this in detail in this presentation.
Awesome. Cool. All right. Well, let's get into it. So just, I guess, real quick, Jason LaFleur, I've been at GTI about 8 years now and kind of lead our sector of residential and commercial building research, and which includes a very large portfolio. But one of the things that we are excited about advancing is hydronic based heating systems like air to water heat pumps. So this is a good alignment for us. If you're not familiar with GTI, just real quick, we are a 501c3 nonprofit that's headquartered outside of O'Hare Airport near Chicago. If you're ever stuck on a layover or coming for the ASHRAE Decarb conference or something, happy to show you around our labs, do a tour, etc. We have footprint around the country with other remote employees and subsidiaries, and we kind of fill a niche between a lot of the maybe earlier stage technology, mid TRL technologies, and advance those through to later stage demonstration, piloting, working between government, state organizations like the California Energy Commission or NYSERDA, and then in bridging that with utilities as well. So kind of work throughout the energy value chain, everything from upstream generation of different types of energy, fuels, electricity, and then the area that Alejandro and I are focused in is, again, in the end use area, sort of the residential and commercial building sector. So this is a little bit about us. The air to water heat pump technology, I think everyone here is familiar with it, so I'm not going to dwell on this. I do like this image from John Siegenthaler that sort of shows the source and sink sides of the equation, and really looking at how we can leverage this platform for advanced technology development, especially as we look at newer generation refrigerants. Having a packaged system is really attractive for that. And the way to get the energy to where you need it is going to be through that water sink conveyor belt. So there's lots of manufacturers out there making these now. This was actually a lot more popping up on the HR floor if you were out in Orlando last year. There's even some fuel-fired technologies. GTI is working with a few of those manufacturers. And again, everything from earlier laboratory scale development and evaluation to field work as well. So in the electric space, a number of out there. I don't have LG on here. Sorry, Mark. I ran out of space on the slide, I guess. But we're going to focus a little bit on one that we've done some work with, a lab study on today, with the Daikin Altherma system for their cold climate rated product offering, and share some of the results we have from that. As I mentioned, we are working with some fuel-fired air-to-water heat pump technologies as well. So these are basically natural gas heat pumps, outdoor or heat pump boilers, I think, as Abby Dakin likes to call them. And what's really interesting about this, not from the technology side, but from the market side, is that we have basically 70 of these that are being piloted right now with the upcoming heating season. Some that were installed last year, some that are being installed in preparation for the upcoming winter, and really generating a lot of very interesting feedback, both from contractor installer perspectives, as well as some of the energy results. And these are all done in partnership with utilities. As you can see, a lot of the logos there. But maybe we can share some of the findings, especially the installer side. I think that will be intriguing regardless of what the engine is being fueled by, the energy side of it. I think there's a lot of installer barriers that are going to be common across electric and gas heat pumps technologies. So more to come maybe in the future on that next year. Our general approach to help advance technologies and evaluate them kind of relies on this three-legged stool of characterizing them through laboratory evaluation, extrapolating results and potential through modeling, and then validating performance and other aspects in the field, right? And that's where we, all these together give us a comprehensive approach to how we work with technology providers to meet market needs. And we're kind of go through this process with the electric air to water heat pump that I'm talking about in detail here. But I think this Venn diagram is a great sort of mental model of how we're trying to understand the potential for anything in the market and what it might do for a given, in this case, a utility customer of ours. So our latest journey in the air-to-water heat pump space is working with the Daikin Altherma product. This is something that's been commercially available in Europe for quite some time. There was actually an early version about a decade ago in the United States that was piloted and pulled from the market. They reversioned it essentially and had with an inclusion for a different refrigerant, R32, which allows them to get to a little bit higher supply water temperatures, and a few different capacities and different configurations on the indoor side. And like many of these systems, they can also call them tri-load or tri-mode systems, where they can do heating, cooling, and hot water. So that's another attraction, I think, for this product category. You got a single heat pump that can serve multiple loads. And they're intending to bring this to market with both the new construction and retrofits, with looking at fan coil units for the air side distribution, or through radiant systems, both possibly existing ones or more likely, like John was alluding to, some of the applications that they're looking at right now and piloting in the field are the in-floor radiant niche as well. But like you said, John, that's a smaller target market for these types of systems. So the question is, how can these grow at scale with broader distribution? So the system that we looked at, it's rated for cold climate performance collectively between the heat pump side and the backup electric resistance element that's in the heat pump, the air to water heat pump. It's an 18 kW system and capable of fairly broad operating ranges that are consistent with much of what we see in North America. So -18 to 95 degrees or so. We actually pushed it further north on the cooling side. I think we went up around where the limit is there, maybe a little bit higher than that. And right, and able to meet capacity at those at that variety of climate performance. However, sometimes it wasn't, we don't see heat pump alone. There is the inclusion of electric, the backup heater as well. So the evaluation that, or the form factor that we evaluated on the indoor side was a integrated storage tank and essentially control hydro box integrated into one unit, as shown on the left. What they've decided to come to market with is a wall hung control box, as you can see on the right there, paired with a separate indirect storage tank. I think that just provides better installer flexibility for various applications, and the ability to have different storage tank sizes as well, depending on occupancy and water draws and things like that. So, but it is sort of this multi-part system where you have the outdoor heat pump unit and indoor components as well. And then the distribution side, many of these air-to-water heat pumps designed to be flexible based on what distribution is available or planned for a given space. The way that we wanted to test this was specifically with an air side distribution system. So for our lab purposes, we used the convector fan coil units that you see sort of in the middle here to pair with the air-to-water heat pump system. So we could understand the forced air delivery side of an application, which I think we feel is most applicable for the North American market. So I'll dig into some of the evaluation details here itself. We have a very complex approach here, and with GTI we have a lab, but we don't do. We're not like a certification lab. We're not doing HRI testing points, and we're trying to understand equipment and develop equipment load performance curves based on various load profiles we run against that equipment. And so in order to do that, we have somewhat complex setup that allows us to have separate. So we have an outdoor environmental chamber where we can take it down really low or really high, and then an indoor chamber where we can control the space and with the fan, where we had the fan coil unit and controlling thermostat, or communicating thermostat, I should say. Sorry. And so in order to make sure that we had enough load going up against that heat pump, we built a separate system outside of our chambers that handles a lot of the heat rejection. And essentially what we did was run a model single family home against this. 3/4 of the heat that was being generated, we were rejecting to the ambient space in the lab versus the amount that was serving the indoor chamber, which was is a small space, and to really characterize how the heat pump unit performs in those various ambient conditions with real loads. So we'll talk a little bit more about that in a minute, but I thought some photos might help first. So we have this outdoor chamber. We've got a unit cooler. We can take it down to -20. And then we now have electric resistance heaters in there to bring up the heat when it needs to offset what the heat pump is putting out. And then on the indoor side, you can see we have that indoor component unit, a fan coil unit. We have some water demand simulators for showering, laundry, etc. simulation, and then a communicating thermostat that was controlling the system from the manufacturer. And then to simulate load, we have a separate system in that space to emulate essentially the envelope losses that the chamber should see at various conditions, as if this was a real single family home. So a lot of times, without some of the test setups and through the CSA standard, et cetera. A lot of this load side is provided by controlling the water temperature, but because of this communicating thermostat and seeing the air side distribution, that research question, we needed to have that separate load generation equipment serving the space as well, to really put the system through its paces, so to speak. So we did some steady state testing on the system and looked at how the heat pump performs compared to some published data from the manufacturer itself, Daikin, shown on the left in the heating side. Sorry for the little bit of a text issue here. And on the cooling side on the right. And generally, I think what we saw was fairly good alignment between what the manufacturer published performance curves were and the test data that we received in the lab setup. So that was encouraging to see. And in some cases, like on the cooling side specifically, it was actually a little bit, there were even a little bit higher than what the performance was indicated from the published data. So we did that first, and then we took that and let's say, well, how does this compare against other manufacturer published data? And so on the left, what we try to do, this isn't always easy to do a comparison with a conventional air-to-air heat pump, but of course, when you're talking with utility customers, they want to know, how does this compare to a mini split? So we did want to try to characterize that against a cold climate air source heat pump mini split system. And so we looked at some published performance data for that system versus the data that we, the data from the air to water system. Not always apples to apples. Like I said, just inherent differences in comparing those types of systems, but at least it's a somewhat of a measuring stick without going to full annual, evaluation. And then comparing to other air to water heat pump systems is a much easier approach. So we looked at one that was using an R410A refrigerant and compared that against what the what the Daikin system was providing here. So I think we do see some improvements with the R32 refrigerant compared to those to that. I think it's somewhat the refrigerant more than other aspects of the system, but encouraging. It's an encouraging trend as we see a move towards advanced refrigerants, I think. So a couple other. This is essentially the steady state comparison of this from our lab data at different leaving water temperatures compared to some of the published data. And you can see links to that those other systems. We looked at a Mitsubishi air-to-air heat pump and a Space Pack air-to-water system for the reference points, and generally see good performance across both those types of conditions. So the on the cool that was the heating side. On the cooling side, somewhat similar results as well on the air to water comparison, but the air to air is, in some cases the air to air is a little bit better at cooling than the air to water system, especially when there's okay. So anyway, the next step we wanted to do was, the way we like to look at equipment is to really evaluate over a single 24-hour period with real loads that are both space heating or cooling and water heating. And the way that we approach this setup, this test approach, is the goal is to accelerate the performance testing so we can get representative day snapshots across the year. And and then extrapolate that through modeling to see what an expected level of performance in the field might be. So we chose some representative daily water draw profiles that were developed from the NREL hot water demand simulator. So you can see like a lot of shower activity in the mornings, some cooking maybe, and laundry activity later in the day, and ran a system against those simulated loads. We also did this with heating and cooling profiles as well. So you see essentially 6 average days. So like this is actually a good example, 65-degree day, which is actually probably an average what we might see in Chicago today. It's going to be close to 80, and then down into the mid 50s at night. So on average, it's a 65-degree day, but you can see how that load would change how the heat pump might need to run across that 24-hour period. And so it's a very mild heating day, as opposed to later in the winter where we would have very more consistently cold and less variation across a 24-hour period based on ambient temperatures that the system would need to respond to, right? So we picked these peak average and we peak winter and average winter and then mild winter days as profiles, and we do the same on the cooling side as well to run the equipment against this 24-hour load, and then do that with and without the water heating to understand the impacts of how the space conditioning side is working, as well as the water heating side of things. So similar picture in terms of instead of ambient outdoor temperature on the y-axis, you're seeing the actual loads that we were running the system up against for those different day periods, right? So now the coldest days are at the top here, highest heating load, and those mild days, like a day like a nice fall day where it might be cold at night, there's a load during the night, and the load goes away, the heating load goes away during the day. So this really helps us characterize equipment and give a good expected level of performance of what we might see in the year, and then based on a given local locality, we can take this results over the course of the year and extrapolate out the number of days that look like this type of average day for Chicago versus Boston versus Madison, Wisconsin, or wherever. And so for the Daikin system, we specifically did this in the applications for the Northeast, and ran this with a simulated single family home. So the single family home that we use here is you can see sort of the load for the home being shown here, and we assumed following NEEP sizing guidance for cold climate heat pumps, determined what the heating load for this building is, and used appropriate local groundwater temperatures as well for the water heating side. And same on the cooling side, right? Basically getting these load profiles for the system that was done, and then looked at, okay, so for this system, we know what the building load is, we know what the design temperatures are, what the indoor set point assumptions are. We looked at applying this within the same home, for both as if this home was in Boston and as if this home was in New York City, and to see what the consumption would be for the equipment in those locations, right? So I can see some of the differences here, in terms of like the peak heating design day of, from ASHRAE. This is coming. This is a 7-degree day, winter design day, and a 13-degree day in New York. We have mixed units here, both Celsius and Fahrenheit, and how that translates to what the peak load is at those conditions. We also wanted to look in, part of the analysis you'll see in the results is looking at costs for this compared to other equipment scenarios, which would essentially be some mixed fuel scenarios, as well as some all electric scenarios. And then not only the cost, but what the greenhouse gas emissions are. And so we use local assumptions for the grids that are serving these two locations here, Boston and New York. All right, so on to results. So based on our load profiles and the equipment performance testing we did, modeling this out over the course of the year in New York, with you can see the electric rates here, basically 22 cents a kilowatt hour and 160 a therm for gas. We compared the system against an 80% furnace or boiler type of application, and then looked at the tri-mode or heat pump here, so the subject of evaluation at different supply water temperatures, what that would be, and essentially that those different supply water temperatures you could think of as a proxy for different distribution types. If it was in-floor radiant heating, you might be able to run at a lower temperature, supply water temperature, versus a forced air application, for example, or a direct radiant application. So, essentially in general, we're seeing, some in almost most of these scenarios, we're seeing savings for the Altherma system compared to the different baseline systems. So that's essentially these last two columns, comparing the two across there. So that's encouraging. I think the one exception was at the higher supply water temperatures, it might not be quite as favorable against a gas boiler. And then take the same approach in Boston, which has a little bit higher electricity rates and natural gas rates. Both utilities are a little more expensive. We didn't comparative propane at all. That's not really wasn't a fuel of interest for this project, or fuel oil or anything like that. But again, pretty good favorable savings on the economics over time in terms of the operational energy costs for the air to water systems. I think one of the challenges with the equipment in general, is good, but what's important to come back to is how this ties back to field testing and also installed costs, which I think many of us it's not a big secret that these systems are pricier than other options on the market. So how do we make the case for this, right? The operational energy savings that I just showed are one way to do that on an ongoing basis, but you still have to overcome that initial first cost and the capital expenses of putting in these systems and the complexity and maybe newness in some markets of HVAC contractors doing more of a plumbing job than a sheet metal or conventional HVAC job like they might be used to. So I think the next step that really characterizing and understanding installed costs are going to be an important part of the overall technology adoption. Something we're looking forward to working with and learning from people like on this call or on this group. So, we do overall, I think there's some good operational energy savings, greenhouse gas emission reduction opportunities, especially even compared to cold climate air source heat pump technologies. I think we're seeing advanced refrigerants helping improve performance, which is encouraging, especially as the industry moves more towards that direction. I think one of the things, and Alejandro, you could probably speak to this a little bit better, we see a big market gap and technology gap with manufacturers, not just Daikin, but others that we've been working with, where there needs to be better integration with air handler units if these are going to be an option for replacing conventional forced air systems. We just don't see very good products in the market, and there's opportunities to improve that. So I kind of mentioned the installed cost barriers. I think 40 to 50K, there was some good work that NEEP did on installed costs for air to water heat pumps. Or I guess the NEEP supported it, but maybe Energy Solutions or somebody did the work. It's a good report. It has a lot of great scenarios in there. But I think as an outcome of things like that, anything that manufacturers can do to help with contractor installation simplification, creating plug-and-play kits, integrating components maybe, or providing flexibility and training, all these things are going to be really important to seeing market success. And finally, I think one of the things that can really help with the economics is some of the demand shifting capabilities that air to water heat pumps have. I know a few months ago, we had Pierre from Harvest speak to the group, and I think he's on the call. We're actually teaming together and literally in the process of signing a contract to start a new project looking at this with NYSERDA. That should be kicking off any week now, to look at how these air to water heat pumps can be paired with dynamic time of use pricing and really help with the economic payback by shifting loads to times when electricity is cheaper, to help overcome some of the cost barriers for the first cost, really leveraging the thermal energy storage capabilities of this type of technology with an integrator like Harvest that can do this. And maybe even in this project specifically, we're also going to be including some of the advanced refrigerant R290 air to water heat pump systems, which show some promise for even more expanded operating temperature ranges than the R32 or other refrigerants. So that's kind of the presentation I wanted to make. I think we're almost at time, so I'll kind of stop and pause for what kind of questions we have, or maybe Alejandro, real quick, you can, if there's any points you want to clarify that I made, or I think that might be good, then we can open it up.
No, I think we'll just wait for any questions.
Yeah, okay.
We have a question from Jeff McGuire about whether or when there's a publication that's coming out on this.
Great question. I think we have something in the hopper for the ASHRAE Winter Conference for next year, which will be in Vegas, I believe, in February. So at that point, we'll have a more detailed study available.
Awesome, thanks. I really like the way you guys did the combination of the modeling and the lab testing here, where you can't really model such a complex system. So yeah, NREL approved good use of BOPT.
I have a question on the modeling versus so you got leaving water temperature results, and you've got already outdoor air temperature profiles for cities, yeah, for like Boston and New York. Couldn't you estimate the load at a given outdoor air temperature for whatever you're assuming and build the profile of leaving water temperature for the outdoor reset and get like your single estimate for what the cost is?
We could. I think part of this in this one, Alejandro, I'll ask you to jump in too, but I'll briefly say that part of what we were looking at here, we couldn't just control the leaving water temperature, I think because of the convector, but Alejandro, you want to add on that?
Yeah, I mean, well, you need to have an understanding how the system works. We're not going to be modeling things that are not truly how the system will be operated in the field. And we like to take into consideration how, best case scenario, an installer does a manual J, has a really good understanding of the load. And based on that, this also has the understanding of the heat rates required for the air handler units or whatever, and that gives you what temperature needs to provide that heat. So it's a lot of variables that need to be considered before you just jump in the model and give the best or the lowest temperature to give you the best COP, right? So that all those considerations are factoring in through the modeling, because again, if you just putting things like, you cannot just go and model something with the lowest air temperature, not understanding that the terminal unit won't give you the capacity needed, right? So there's all those constraints are needed, and also understanding how there's a shift between load and ambient temperature, and despite load being very close to ambient temperatures, there's some shifts. It could be within 20% or more for different factors. And all that, it's very, it's very well understood through these evaluations, so we can have a better understanding of part load relative to all those different factors.
Okay, thanks. Other questions? Okay. Well, thank you very much, Jason and Alejandro. Appreciate the presentation. Share my slides again.
Yeah, absolutely. And I'll let the group know when we do have something that's published to follow up on that.
Sounds good. So, as usual, we are always looking for speakers in the upcoming meetings. I know that the next meeting will fall sort of amid the conference season. I am particularly interested in talking to folks about upcoming standards. Maybe we could have Abby Dakin stop by or ask her colleagues to stop by to talk about upcoming standards. I also, we talked about this at the beginning of the meeting, but anybody who can put together a good presentation on distribution optimization and distribution options, I think that would be particularly compelling as a presentation to the group. It sounds like the research on that is a few steps down the road at this point, because everybody's jumping into their interviews and looking for data. But I'd look forward to that if somebody had something they could present. I think I have figured out the listserv situation. I think it would be extremely valuable to be able to just email the group about questions. We have a listserv for the power group in California that's on panels, and that has tons of activity. Listservs are surprisingly not super straightforward, and you can't do them like right out of even Business Outlook. So I'm getting my IT to set something up. So look forward to that. It might not be the Advanced Water Heating Initiative URL, but it'll be something similar that I sent along. Feel free to email me your ideas. Tentatively, the next meeting is October 24th. So please stop by for that and mark your calendar. Does anybody have anything else that they wanted to bring up before the end of the meeting? All right. Well, thank you everybody for joining this meeting. Have a good weekend, and maybe you'll see each other around all these fall conferences. Bye, everyone.
Thank you. This is great.
Thanks, John.
Have a great weekend.
Thank you.